Welcome to Chapter 2, Video 1, covering the first half of Section 2.1. This section is a bit long, so I split it into two shorter videos rather than one super long video. We have 4 objectives for this video. First, we want to remind ourselves what an element is and how we can identify elements based on their symbols. We want to be able to tell the difference between elements and compounds. We want to know why minerals are important in the human body. And we want to talk about radioactivity and how it can be very helpful as a tool in some situations or very harmful in other situations. So, you guys have seen the periodic table since probably 6th grade science, if not earlier. Okay, so an element is anything that has its own tile on the periodic table. And elements have their own unique chemical properties, and they're the simplest form of matter. Elements are identified by their atomic number, which is the number of protons in the nucleus. So an atom of carbon will always have 6 protons in the nucleus. An atom of hydrogen will always have 1 proton in the nucleus. If we do some sort of nuclear fission or nuclear fusion reaction and change the number of protons in the nucleus, we have a different element. Okay, so the number of protons always tells the identity of the element. The periodic table is arranged by atomic number, starting with our smallest atomic number, hydrogen, 1 proton in the nucleus, and all the way up into very large atoms that have over 100 protons in the nucleus. The elements all have a 1 or 2 letter symbol, and we have 24 elements that have biological roles in the body, meaning our body uses them to do something. Of those 24, 6 elements account for 98.5% of a human's body weight. The remaining 18 elements are found in very, very small amounts, but still have very important roles in human body function. Minerals can be defined as inorganic elements that come from the soil. They move from the soil into plants and then are passed up the food chain to humans, either when humans eat the plants or when humans eat animals that ate the plants. The minerals that we're concerned about in the human body are calcium, phosphorus, chlorine, magnesium, potassium, sodium, and sulfur. And you see those abbreviations right there. Some of them are not super intuitive, and these are ones that you're going to be seeing fairly often. I'm going to recommend that you guys go ahead and memorize what those elements, what elements correspond to those abbreviations. Altogether, these account for 4% of human body weight. Calcium takes up the largest percentage of this because there's so much calcium in your bones. One of the things that these minerals are really important for is in enzymes. There are a lot of enzymes that have a core of magnesium or a core of sulfur, or have sulfur bridges that link the enzyme subunits together. And some of these minerals that are circulating through the body are electrolytes that we use for nerve and muscle function. So potassium and sodium and chloride and calcium are definitely part of our electrolyte balance system. So now we're going to move on and talk about what atoms look like. So back in the early 1900s, a scientist named Niels Bohr proposed something called the planetary model. And it really is just a model. It has some very useful features and then some features that we have found to be inaccurate. The useful features we continue to use today, but I want to make it very clear that the planetary model does not reflect what we would actually see if we had a microscope powerful enough to drill down and look at an individual atom. And we'll talk more about that in just a moment. If we were to look at an atom, we would find that the nucleus is in the center. And the two subatomic particles that we find in that nucleus are the protons and the neutrons. Protons have a mass of 1 atomic mass unit and a positive charge. Neutrons have no charge. They are neutral neutrons, and also have a mass of 1 atomic mass unit. So a couple notes here. Atomic mass unit is a totally made up unit. But to use any of our standard units like grams or pounds or anything like that, we would be working with such tiny decimals of numbers that it would just be maddening. So scientists made up a unit called the atomic mass unit, and it equals the mass of 1 proton. So protons and neutrons are equal in mass. Protons positive, neutrons neutral, no charge, and they're both found in the nucleus. Electrons are found in clouds circling the nucleus. Okay, and this is where Niels Bohr disagreed a bit with what we've found since 1913. Electrons are found in clouds of varying densities. Electrons, compared to protons and neutrons, are very small, even compared to tiny protons and neutrons. So we don't calculate the mass of electrons when we're finding the mass of an atom. They do have a very tiny mass, but we would need so many electrons before it would even round up to 0.1 atomic mass units that we just round down to 0 as a rule for electrons. And electrons are negative. So if we have an equal number of protons and electrons in a given atom, the protons, positive, balance out the negative electrons, and we can say that that atom is neutral. Neutrons don't play a role in determining if an atom is positive, negative, or neutral, because neutrons don't have a charge at all. It's very important to understand what a valence electron is. Okay? When we have the electrons organized in the cloud that surrounds the nucleus, some of those electrons will be in the outside of the cloud and some will be on the inside. The ones on the outside are called valence electrons. They're furthest away from the nucleus where the protons and the neutrons are. Those valence electrons are the ones that are able to participate in chemical bonding. Okay, so the core electrons close to the protons and the neutrons don't participate in chemical bonding. Only the valence electrons are able to do that. And here we have a comparison of the Bohr model and then what we believe to be the modern atomic model. So in the Bohr model, you can see that the electrons are thought to be circling the nucleus like planets circle the sun. And there are some things about this model that make it very convenient. We can see the outer shells here. These outer shells, it's very easy to tell how many electrons are in the outside shell or how many valence electrons we're going to be dealing with in chemical bonding. The more accurate depiction is over here, the modern atomic model, and it shows that electrons are found in clouds surrounding the nucleus, and we can never know the exact position of an electron. However, we can calculate the probability of an electron being found in a particular place. So there are benefits and drawbacks to both of these models. The Bohr model lets us see these valence electrons pretty clearly, but this is not how an atom would actually look in real life. So I want to make it very clear, this is a model and not an actual depiction. We'll look at the second half of section 2.1 in the next video.